I'm Hao Shen in November Lab from Chicago. Today, I will share with you the efficient computation of expected pairwise coalescent times in the structured coalescent. So, a structured coalescent is an extension of standard coalescent. In standard coalescent, you have lineages coalesce in the parametric population. In the structured coalescent, apart from coalescence, we also have a lineage migration. So here you can see that lineages can migrate to the neighboring demes, and when they are in the same deme, they can coalesce. The structured coalescent, we can parameterize structured coalescent use a matrix of a transition rate matrix, which encode the migration of lineages. And here, this is the form of this transition rate matrix Q. And the Laplacian of the corresponding weighted graph is then simply minus Q. So when the lineages are in the same deme, there are additional coalescence rates for each pair of lineages. They're encoded in a vector we call gamma. So with these parameters, we have a stochastic process, and we have a class of important random variables, which basically the pairwise coalescent times. Here we call Tij the pairwise coalescent time between lineages starting from deme I and a lineage starting from deme J. So they'll have to migrate until they're in the same deme, and some probability of coalesce. If they do not coalesce, they can migrate again. What we want to study here is the expected pairwise coalescent time, which is like capital Tij. Why do we want to study this? Two reasons. First, it's a family of important quantities in the structured coalescent theory. They are theoretically important by their own. Second, this quantity is related to the covariance structure of the observed allele states. I noticed that some of the talks has already mentioned the relationship between FST and the coalescent times. Here is just another illustration. If you condition on only have one mutation, the covariance structure of these allele states are tightly related to these expected pairwise coalescent times. This is the equation for the expected pairwise coalescent times. D is the deme number. Gamma is the vector we introduced just now. And T is a D by D matrix of expected pairwise coalescent times across demes. And L is the graph Laplacian or the negative transition rate matrix constructed from lineage and backward migration rates. So here is a short derivation of this. So you just think about the small time interval delta t, and then this Tij, you can think about either the first lineage migrate with certain probability, or the second lineage migrate with certain probability, or they stay in the deme. But when they are in the same deme, which means if I equal to j, there is additional probability of coalescence. That's why you have this delta function, delta ij, gamma. And let this delta t goes to 0, and you can write the equation in the matrix format. We'll get the desired form. This equation has been discovered multiple times in history. Okay, so one problem with respect to this equation is how to efficiently compute this t from gamma and L. This will not be a problem if you just compute it once, but in actual inference, we typically need to compute this type of equation many, many times. So that's why we need efficient computation. So if you directly vectorize this equation, you'll have d square, order of d square variables. And for a linear equation with order of d square variables, the complexity will be d to the 6. And this is usually computationally prohibitive. Or you can use it's a very popular method called isolation by resistance. Use approximation based on that. You can reduce the computational complexity to d cubed. But this typically has very strong assumption about the form of migration. You have to assume migration is symmetric or reversible, isotropic, or like that. So these problems arise in the actual inferences, there are currently there are two types of inferences. And you can see there is a trade-off. Either you have fine resolution and symmetric migration, like EAMs and FEAMs. A fine resolution means you have many, many DEAMs. Or you allow asymmetric migration, but limit yourself to coarse resolution, like which is done by Landgren and Rolf in 2019. Here you only have 9 DEAMs. And the reason that you have these two different methods is they use different computational approaches to the previous problem. However, we know that asymmetric migration on gene flow is very common. You can either have migration driven by directional forces like prevailing winds or the ocean currents or demographic and historical factors like human range expansion. And these migration can happen across many, many DEAMs, not just like 10 DEAM or something like that. So that's why we want to try something that is completely different. We want to know whether it's possible to directly solve this equation at an acceptable complexity. The answer is yes, and we would like to solve the more general equation. So the right-hand side is not just one, but an arbitrary symmetric matrix, and we can solve this with time complexity d to the 4th. So the first thing we notice is that this equation is closely related to an equation we know how to solve, which we call the continuous Lyapunov equation. But these equations can be solved exactly with complexity d cubed using what we know as the Bartle-Stewart algorithm. If this A is symmetric and either this L or minus L is what we call stable matrix, which means that all eigenvalues have positive real part. So this is something we have at hand. We know how to solve it very efficiently. In our case, it's slightly different for 2 points. First, our matrix is a matrix Laplacian minus L. This is not a stable matrix, it's a semi-stable. However, the good part is that we know the structure of the singularity. So assume it's a fully connected graph, the only eigenvalue with non-positive real part is basically 0. And with here, we call this Z, which is basically a vector of 1 as its corresponding right eigenvector, and pi, the stationary distribution, as its left eigenvector. The second thing is that we have these additional diagonal terms, which is basically the coalescence rates, diag gamma and diag x. So if we can successfully address these two problems, we can solve this equation. So let's first solve the first problem. Here, this minus L is a semi-stable instead of stable matrix. In this case, we cannot just solve this equation Lx plus XL transpose minus A equal to 0 for arbitrary matrix because A might not be in the range of the operator. It's a singular operator. But we can solve it in the least square sense, which means that we solve the equation Lx plus XL transpose equal to A and project onto the operator. This projection is in general not easy to compute directly, but we can compute it using an indirect method. We first project it onto the orthogonal complement and then use A to minus this projection. Okay, so what's the orthogonal complement? So let's say Y is an element in the orthogonal complement, and we have an element in this range of the operator Lx plus XL transpose. And then if you want to look at their product, it's product of two matrices, so it's a sum of the entry-wise product. So it's a trace of their matrix product. And use some techniques of trace computation, you can always switch the order. And we can show that this orthogonal complement is basically the kernel of the conjugate operator, L transpose times something plus something times L. This kernel can be easily computed. The orthogonal complement is the kernel of this conjugate operator, and this kernel is simply the pi transpose pi, where pi is a stationary distribution. Here we use pi hat. It's a normalized stationary distribution. It's easy to do projection. Okay, so now we know how to project it onto the orthogonal complement. then the projection is simply A minus its projection onto the orthogonal complement. And we have the equation Lx plus LXL transpose equal to A projection. And this is, we just need to solve it exactly instead of in the least square sense. How to solve this? Well, we can do so by first do a linear transformation or change of basis. So let this P1 to be a vector of all one with some normalization step and extend it to an orthonormal matrix. And then after we change of basis, we'll have a new matrix L prime with the first column being 0. And this is very nice because by doing so, the equation we have previously becomes 2 equations. And the second equation is very nice because now we go from a d-dimensional equation to a minus 1-dimensional equation, which is not singular anymore. This minus L22 prime is now a stable matrix. So we can first solve the second equation and replace this x22 prime into the first equation and solve this. Okay, so we now solve the first problem. Minus L is semi-stable instead of stable, it's solved. Now we deal with additional terms. We have this diag gamma, diag x stuff. The way we deal with this is we write the solution as a linear combination of the solution to the equation we already know how to solve. So we first solve the following equations: Lx plus XL transpose equal to G, and Lx plus XL transpose equal to EI. Here, EI is the matrix with its ith entry being 1 and other being 0. And these are the equations we use to deal with the diagonal. So these equations already know can be solved in the least square sense. And solving these in the least square sense is equivalent to solving the second part exactly. And we know how to solve it. Okay, the final solution is to assume to be a linear combination of these solutions. And Z, here Z is a matrix of all 1. We add this because this is in the kernel of the operator. Okay, now we can replace all of these formats into the original equation. And we have actually d plus 1 unknown coefficients, and we want to solve them. So what's the d plus 1 equation? The first equation is that the projection onto the orthogonal complements just cancels out. And then we check the equation for the diagonal elements. There are d diagonal elements, which just give us the equation. This is the first equation. The projection cancels out. And this is the rest d equations, which is the diagonal elements. Okay, so now we have d plus 1 equations for d plus 1 unknown. This can be written in the matrix format. Here, just pi I is just the ith entry of the stationary distribution. And this is just a matrix equation, and we can solve it. Okay, so what's the complexity? We solve d singularly Lyapunov equation. Each can be solved with the complexity d cubed. And in total, we have a complexity d to the 4th. Up to now, it sounds like we just solve a mathematical problem, but these as we showed before, these mathematical problems are tightly related to inference method. And the key distinction between the previous inference method is different approaches to attack this mathematical problem. Now we have a new and more powerful method to solve this. Well, very naturally, we can develop a new inference method. So we have already solved this class of generalized Lyapunov equation exactly with time complexity O d to the 4th. And combining this with the panelized maximum likelihood approach, we develop a new inference method called FRAME, which stands for Fine Resolution Asymmetric Migration Estimation. On the right-hand side is a comparison of our method with a direct computing method. And you can see that our method is much faster than the direct method. Here, I will show you a glimpse of what our method can actually do. So here is the ground truth of a simulation. On the left-hand side is a full graph which shows all the edges with strands of the migration represented by the color, blue representing strong migration and yellow representing weak migration. On the right-hand side is another representation we call the difference graph, which if you have a migration rate from A to B larger than that from B to A, we will just draw an edge from A to B. And with color representing its direction and the strength represented by the transparency, the log difference. We always say the strength of the asymmetries. This is a ground truth case, and you can simulate these kind of migration scenario with MS Prime, and then fit this the genotypes generated by this migration scenario. You can see that it's a rather complicated migration scenario. You have lineages converging to a point, diverging from a point. You have lineages directionally migrating. You have cycles. So even this extremely complicated migration scenario, our method was able to recover these patterns very faithfully. Okay, so we also apply our method to the empirical data set. This is two data sets. One data set is a data set previously used by Themes of the American gray wolf, and another data set is the populous data set. This is a data set used by Peter Rolfe et al. And you can see that in the wolf case, frame increase the R square of the fitted genetic distance versus empirical genetic distance a little bit, which means that in the wolf data set, symmetric migration is a rather reasonable assumption. However, in the populous data set, we see the R square improve from 0.869 to 0.989. It's a huge improvement. And look, if you just look at the difference graph, at the top of this graph, you'll see a stream of directionally migrating lineages. And this asymmetry is consistent with what we know about the populous biology. In the original paper, they also find this asymmetric gene flow. So this indicates that in this populous case, this asymmetric gene flow should not be neglected. Okay, so let's go to discussion. So currently we are solving this equation exactly. And as we know, there is a very common method to solve this large-scale equation, which is the iterative method. They are typically much faster than exact method in the well-conditioned cases. But in the ill-conditioned cases, a suitable preconditioning strategy is necessary for the numerical stability. And we are currently experimenting with that. And second is, well, that's another very interesting area. Pairwise coalescent times are defined only when lineages are sampled contemporaneously. In heterocurrence that coalescent, the relevant quantities are the branch lengths. Although techniques developed here can be helpful in those cases, related computational problems are in general more complicated and which requires new theory and method for those cases. Okay, I would like to thank all the November lab members and the population genetics computational biology group in U Chicago. Thank you.
I have a minute and a half for questions. Nick.
Yeah, so it's a really neat sort of computational method, but it does assume equilibrium. And I wonder if there's power to distinguish alternative explanations, for example, admixture or some non-equilibrium process. Could you tell the difference?
The short answer is no. Well, maybe there are some signals. For example, in some extreme non-equilibrium case like range expansion, you'll see that the range of the migration is very large. The asymmetry is very, very large, let's say across 5 different magnitudes. So that could be a signal. And we do have those simulations, which I do not show. But you're right, it's an equilibrium method. Currently, what you are doing is to fit those non-equilibrium settings using an equilibrium method. A better way is, like what I said in the last point, is to directly model in those non-equilibrium settings. But there are actually also, it's not similar, but a more complicated computational issues there.